All right, we are back again reading Python Programming by John Zell. This is the third edition, and we are in Chapter 4, Section 4. 4.4 says using graphical objects. Let's dive right in. Some of the examples in the above interactions may look a bit strange to you. To really understand the graphics module, we need to take an object-oriented point of view. Remember, objects combine data with operations. Computation is performed by asking an object to carry out one of its operations. In order to make use of objects, you need to know how to create them and how to request operations. In the interactive examples above, we manipulated several different kinds of objects: graph win, point, circle, oval, line, excuse me, text, and rectangle. These are examples of classes. Every object is an instance of some class, and the class describes the properties the instance will have. Borrowing a biological metaphor, when we say that Fido is a dog, we are actually saying that Fido is a specific individual in the larger class of all dogs. In OO terminology, Fido is an instance of the dog class. Because Fido is an instance of this class, we expect certain things. Fido has 4 legs, a tail, a cold, wet nose, and he barks. If Rex is a dog, we expect that he will have similar properties, even though Fido and Rex may differ in specific details such as size or color. The same idea holds for our computational objects. We can create 2 separate instances of point, say P and P2. Each of these points has an x and y value, and they both support the same set of operations like getX and draw. These properties hold because the objects are points. However, different instances can vary in specific details, such as the values of their coordinates. To create a new instance of a class, we use a special operation called a constructor. A call to a constructor is an expression that creates a brand new object. The general form is as follows. Here's some code. We have a left-facing arrow, class-name, right-facing arrow, open parentheses, left-facing arrow, param1, right-facing arrow, comma, left-facing arrow, param2, right-facing arrow, comma, or probably and continue on in this manner, and then end in parentheses. Here, the class name is the name of the class that we want to create a new instance of, for example, circle or point. The expressions in the parentheses are any parameters that are required to initialize the object. The number and type of parameters depend on the class. A point requires 2 numeric values, while a graph win can be constructed without any parameters. Often a constructor is used on the right side of an assignment statement, and the resulting object is immediately assigned to a variable on the left side. That is then used to manipulate the object. To take a concrete example, let's look at what happens when we create a graphical point. Here is a constructor statement from the interactive example above. P equals point, open parentheses 50, 60, end parentheses. So that's going to draw a point on the win. The constructor for the point class requires 2 parameters, giving the x and y coordinates for the new point. These values are stored as instance variables inside the object. In this case, Python creates an instance of point having an x value of 50 and a y value of 60. The resulting point is then assigned to the variable p. A conceptual diagram of the result is shown in figure 4.4. I can show that to you now. Here is figure 4.4. Hopefully you can see it in your book on page 92. The variable p refers to a new point. So the next paragraph, to perform an operation on an object, we send the object a message. The set of messages that an object responds to are called the methods of the object. You can think of methods as functions that live inside the object. A method is invoked using dot notation. So we have a left-facing arrow, object, right-facing arrow, dot, left-facing arrow, method dash name, right-facing arrow, open parentheses, left-facing arrow, param 1, right-facing arrow, comma, left-facing arrow, param 2, right-facing arrow, comma, dot, 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 and parentheses. The number and type of the parameters is determined by the method being used. Some methods require no parameters at all. You can find numerous examples of method invocation in the interactive examples above. As examples of parameterless methods, consider these two expressions, p.getX, empty parentheses, and p.getY, end parentheses. The getX and getY methods return the x and y values of a point respectively. Methods such as these are sometimes called accessors because they allow us to access information from the instance variables of the object. Page 93. Other methods change the values of an object's instance variables, hence changing the state of the object. All of the graphical objects have a move method. Here is a specification. Move, open parentheses, dx, comma, dy, end parentheses, colon, moves the object's dx units in the x direction and dy units in the y direction. To move the point P to the right 10 units, we could use this statement. P.move, open parentheses, 10, comma, 0, end parentheses. This changes the x instance variable of p by adding 10 units. If the point is currently drawn in a graph win, move will also take care of erasing the old image and drawing it in its new position. Methods that change the state of an object are sometimes called mutators. The move method must be supplied with two simple numeric parameters indicating the distance to move the object along each dimension. Some methods require parameters that are themselves complex objects. For example, drawing a circle into GraphWin involves two objects. Let's examine a sequence of commands that does this. Here's the code. Circ equals circle, open parentheses, point, open parentheses, 100, comma, 100, end parentheses, comma, 30, end parentheses. New line, win equals graph win, empty parentheses. New line, circ.draw, open parentheses, win, end parentheses. The first line creates a circle with a center located at the point 100, 100, and a radius of 30. Notice that we used the point constructor to create a location for the first parameter to the circle constructor. The second line creates a graph win. Do you see what is happening in the third line? This is a request for the circle object circ to draw itself into the graph win object win. The visible effect of this statement is a circle in the graph win centered at 100, 100 and having a radius of 30. Behind the scenes, a lot more is happening. Remember, the draw method lives inside the circ object. Using information about the center and radius of the circle from the instance variables, the draw method issues an appropriate sequence of low-level drawing commands, a sequence of method invocations to the graph win. A conceptual picture of the interactions among the point, circle, and graph win objects is shown in figure 4.5. Fortunately, we don't usually have to worry about these kinds of details. They're all taken care of by the graphical objects. We just create objects, call the appropriate methods, and let them do the work. That's the power of object-oriented programming. Let's take a look at object or figure 4.5. This one is figure 4.5. I hope you can find it in your book. If you're following along, it's at the top of page 94. And we have the circle and the graph win and the point. And we have object interactions to draw a circle. There is one subtle gotcha that you need to keep in mind when using objects. It is possible for two different variables to refer to exactly the same object. Changes made to the object through one variable will also be visible to the other. Suppose, for example, we are trying to write a sequence of code that draws a smiley face. We want to create two eyes that are 20 units apart. Here is a sequence of code intended to draw the eyes. Here's the code. Hashtag, incorrect ways to create two circles. New line. Left eye equals circle, open parentheses, point, open parentheses, 80, 50, end parentheses, 5, end parentheses. New line. Left eye dot set fill, open parentheses, single quote, yellow, single quote, end parentheses. New line. Left eye dot set outline, open parentheses, single quote, red, single quote, end parentheses. New line. Right eye equals left eye. New line. Right eye dot move, open parentheses, 20, 0, end parentheses. The basic idea is to create the left eye and then copy that into a right eye, which is then moved over 20 units. This doesn't work. The problem here is that only one circle object is created. The assignment, right eye equals left eye, simply makes the right eye refer to the very same circle as left eye. Figure 4.6 shows the situation. When the circle is moved into the last line of code, both right eye and left eye refer to it in its new location on the right side. This situation where two variables refer to the same object is called aliasing. It's got an alias, aliasing. And it can sometimes produce rather unexpected results. So we had the left eye and the right eye both being the same circle. It just changed names. Now we've got two names for the same object. We don't have actually two objects. I hope you're following along. One solution to this problem would be to create a separate circle for each eye. Hashtag, a correct way to create two circles. New line. Left eye equals circle, open parentheses, point, open parentheses, 80, 50, end parentheses, 5, end parentheses. New line. Left eye dot set fill, open parentheses, single quote, yellow, single quote, end parentheses. New line. Left eye dot set outline, open parentheses, single quote, red, single quote, end parentheses. New line. Right eye equals circle, open parentheses, point, open parentheses, 100, 50, end parentheses, 5, end parentheses. New line. Right eye dot set fill, open parentheses, single quote, yellow, single quote, end parentheses. New line. Right eye dot set outline, open parentheses, single quote, red, single quote, end parentheses. This will certainly work, but it's cumbersome. We had to write duplicated code for the two eyes. That's easy to do using a cut and paste approach, but it's not very elegant. If we decide to change the appearance of the eyes, we will have to be sure to make the changes in two places. The graphics library provides a better solution. All graphical objects support a clone method that makes a copy of the object. Using clone, we can rescue the original approach. Here we go with the next code. Hashtag, hashtag, correct ways to create two circles using clone. New line, left eye equals circle, open parentheses, point, open parentheses, 80, 50, end parentheses, 5, end parentheses. New line, left eye dot set fill, open parentheses, single quote, yellow, single quote, end parentheses. New line, left eye dot set outline, open parentheses, single quote, red, single quote, end parentheses. And then we either have new page or new line. Let's find out. New line. Right eye equals left eye dot clone, empty parentheses. Hashtag right eye is exact copy of the left. New line. Right eye dot move, open parentheses, 20, 0, end parentheses. Strategic use of cloning can make some graphics tasks much easier. All right, now we're on to section 4.5 that says graphing future value. Now that you have some idea of how to use objects from graphics, we're ready to try some real graphics programming. One of the most important uses of graphics is providing a visual representation of data. They say a picture is worth 1,000 words. It is almost certainly better than 1,000 numbers. Just about any program that manipulates numeric data can be improved with a bit of graphical output. Remember, the program in Chapter 2 that computed the future value of a 10-year investment? Let's try our hand at creating a graphical summary. Programming with graphics requires careful planning. You'll probably want pencil and paper handy to draw some diagrams and scratch out calculations as we go along. As usual, we begin by considering the specification of exactly what the program will do. The original program, futval.py, had two inputs. The amount of money to be invested and the annualized rate of interest. Using these inputs, the program calculated the change in principal year by year for 10 years using the formula principal equals principal plus, open parentheses, 1 plus APR, end parentheses. It then printed out the final value of the principal. In the graphical version, the output will be a 10-year bar graph where the height of successive bars represents the value of the principal in successive years. Let's use a concrete example for illustration. Suppose we invest $2,000 at 10% interest. Table 4.1 shows the growth of the investment over a 10-year period. Our program will display this information in a bar graph. Figure 4.7 shows the same data in graphical form. The graph contains 11 bars. The first bar shows the original value of the principal. For reference, let's number these bars according to the number of years the interest accrued, 0 through 10. Here is a rough design for the program. Print an introduction, get value of principal and APR from user, create a graph win, draw scale labels on left side of window, draw a bar at position 0 with height corresponding to principal. Now we have table 4.1. This is a table showing the growth of $2,000 at 10% interest. You can likely see this in your book as well at the top of page 97. For successive years 1 through 10, calculate principal equals principal asterisks, open parentheses, 1 plus APR, end parentheses. New line, draw a bar for this year having a height corresponding to principal. Wait for user to press enter. The pause created by the last step is necessary to keep the graphics window displayed so that we can interpret the results. Without such a pause, the program would end and the graph win would vanish with it. While this design gives us the broad brush strokes for our algorithm, there are some very important details that have been glossed over. We must decide exactly how big the graphics window will be and how we will position the objects that appear in this window. For example, what does it mean to draw, say, a bar for year 5 with a height corresponding to $3,221.02? Let's start with the size of the graph win. Recall that the size of a window is given in terms of the number of pixels in each dimension. Computer screens are also measured in terms of pixels. The number of pixels, or resolution, of the screen is determined by the monitor and graphics card in the computer you use. The lowest resolution screen you are likely to encounter on a personal computer these days is a so-called extended VGA screen that is 1024 by 768 pixels. Most screens are considerably larger. Our default 200 by 200 pixel window will probably seem a bit small. Let's make the graph win 320 by 240. That will make it about 1/8 the size of a small screen. Here is figure 4.7. It's showing a graph, that chart looking thing on here, this, at the top of page 98. Given this analysis, we can flesh out a bit of our design. The third line of the design should now read, create a 320 by 240 graph win titled, single quote, investment growth chart, single quote, single quote. You may be wondering how this will translate into Python code. You've already seen that the graph win constructor allows an optional parameter to specify the title of the window. You can also supply width and height parameters to control the size of the window. Thus, the command to create the output window will be win equals graph win, open parentheses, quote, investment growth chart, end quote, comma, 320, comma, 240, end parentheses. Next, we turn to the problem of printing labels along the left edge of our window. To simplify the problem, we will assume the graph is always scaled to a maximum of $10,000, with the 5 labels 0.0k to 10.0k as shown in the example window. The question is, how should the labels be drawn? We will need some text objects. When creating text, we specify the anchor point, the point the text is centered on, and the string to use as the label. The label strings are easy. Our longest label is 5 characters, and the labels should all line up on the right side of a column, so the shorter strings will be padded on the left with spaces. The placement of the labels is chosen with a bit of calculation and some trial and error. Playing with some interactive examples, it seems that a string of length 5 looks nicely positioned in the horizontal direction, placing the center 20 pixels in from the left edge. This leaves just a bit of white space at the margin. In the vertical direction, we have just over 200 pixels to work with. A simple scaling would be to have 100 pixels represent $5,000. That means our 5 labels should be spaced 50 pixels apart. Using 200 pixels for the range 0 to 10,000 leaves 240 minus 200 equals 40 pixels to split between the top and the bottom margins. We might want to leave a little more margin at the top to accommodate values that grow beyond $10,000. A little experimentation suggests that putting the 0.0k label 10 pixels from the bottom, position 230, seems to look nice. Elaborating our algorithm to include these details, the single step, draw scale labels on the left side of window, becomes a sequence of steps. Here's the code. Draw label, open quote, 0.0k, end quote, at open parentheses 20, comma 230, end parentheses. New line, draw label, open quote, 2.5K, end quote, at open parentheses 20, comma 180, end parentheses. New line, draw label, open quote, 5.0K, end quote, at open parentheses 20, comma 130, end parentheses. New line, draw label, open quote, 7.5K, end quote, at open parentheses 20, comma 80, end parentheses. New line, draw label, open quote, 10.0K, end quote, at open parentheses 20, comma 30, end parentheses. The next step in the original design calls for drawing the bar that corresponds to the initial amount of the principal. It is easy to see where the lower left-hand corner of this bar should be. The value of $0, $0.0, is located vertically at pixel 230. And the labels are centered 20 pixels from the left edge. Adding another 20 pixels gets us to the right edge of the labels. Thus, the lower left corner of the 0th bar should be at location 40, 230. Now, we just need to figure out where the opposite upper right-hand corner of the bar should be so that we can draw an appropriate rectangle. In the vertical direction, the height of the bar is determined by the value of principal. In drawing the scale, we determine that 100 pixels is equal to $5,000. This means that we have 100 divided by 5,000 equals 0.02 pixels to the dollar. This tells us, for example, that a principal of $2,000 should produce a bar of height 2,000, inside parentheses 0.02, equals 40 pixels. In general, the Y position of the upper right corner will be given by 230 minus principal 0.02. Remember that 230 is the 0 point, and the Y coordinates decrease as they go up. How wide should the bar be? The window is 320 pixels wide, but 40 are eaten up by the labels on the left. That leaves us with 280 pixels for 11 bars. 280 divided by 11 equals 25.4545. Let's just make each bar 25 pixels. That will give us a bit of margin on the right side. So the right edge of our first bar will be at position 40 plus 25. That equals 65. We can now fill in the details for our drawing, the first bar into our algorithm. It will look like this. Draw a rectangle from 40, 230 to 65, 230 minus principal asterisk 0.02, end parentheses. At this point, we have made all the major decisions and calculations required to finish out the problem. All that remains is to percolate these details into the rest of the algorithm. Figure 4.8 shows the general layout of the window with some of the dimensions we have chosen. I'll show you figure 0.8. It's in the middle of the page. What a lovely graph. Let's figure out where the lower left corner of each bar is going to be located. We chose a bar width of 25. So the bar for each successive year will start 25 pixels farther right than the previous year. We can use a variable year to represent the year number and calculate the x-coordinate of the lower left corner as year 25 plus 40. The plus 40 leaves space on the left edge for the labels. Of course, the y-coordinate of this point is still 230, the bottom of the graph. To find the upper right corner of a bar, we add 25, the width of the bar, to the x value of the lower left-hand corner. The y value of the upper right corner is determined from the updated value of principal, exactly as we determined it for the first bar. Here's the refined algorithm. You ready for the code? For year running from a value of 1 up through 10, new line, calculate principal equals principal asterisks, open parentheses 1 plus APR end parentheses, new line, calculate x 11 equals 25 asterisk year plus 40, new line, calculate height equals principal asterisk 0.02, new line, draw a rectangle from open parentheses x11, 230 end parentheses, 2 open parentheses x 11 plus 25, 230 minus height end parentheses. The variable x11 stands for the x lower left, the x value of the lower left corner of the bar. Putting all this together produces the detailed algorithm shown below. Here's the code. Print an introduction. Get value of principal and APR from user. Create a 320 by 240 graph win titled single quote, investment growth chart, single quote. New line, draw label, open quote, 0.0K, end quote, at parentheses 20, 230, end parentheses. New line, draw label, quote, 2.5K, end quote, at open parentheses 20, 180, end parentheses. New line, draw label, quote, 5.0K, end quote, at open parentheses 20, 130, end parentheses. New line, draw label, open quote, 7.5K, end quote, at open parentheses 20, 80, end parentheses. New line, draw label, open quote, 10.0K, end quote, at open parentheses 20, 30, end parentheses. New line, draw a rectangle from open parentheses 40, 230, end parentheses, to open parentheses 65, 230, minus principal asterisk 0.02, end parentheses. New line, for year running from a value of 1 up through 10, new line, calculate principal equals principal asterisk, open parentheses, 1 plus APR, end parentheses. New line, calculate x11 equals 25 asterisk, year plus 40. Draw a new line, draw a rectangle from open parentheses x11, 230, end parentheses, to open parentheses x11 plus 25, 230, minus principal asterisk 0.02, end parentheses. Wait for new line, wait for user to press enter. Whew, that was a lot of work, but we're finally ready to translate this algorithm into actual Python code. The translation is straightforward, using objects from the graphics library. Here is the program. Goodness, I don't know if you're sleepy, but I'm sleepy. We're going to have to finish this chapter tomorrow. All right, that was a lot of work. We can translate this. Here is the program. Hashtag footval underscore graph.py. New line from graphics, import, asterisk. New line, def main, empty parentheses, new line, hashtag, introduction, new line, print, open parentheses, open quote, This program plots the growth of a 10-year investment period, end quote, end parentheses. New line, hashtag, get principal and interest rate. New line, principal equals float, open parentheses, input, open parentheses, open quote, enter the initial principal, colon, end quote, end parentheses, end parentheses. New line, APR equals float, open parentheses, input, open parentheses, open quote, enter the annualized interest rate, colon, end quote, end parentheses, end parentheses. New line, hashtag, create a graphics window with labels on left edge. Win equals graph win, open parentheses, quote, investment growth chart, end quote, comma, 320, comma, 240, end parentheses. New line, win dot set background, open parentheses, open quote, white, end quote, end parentheses. New line, text, open parentheses, point, open parentheses, 20, comma, 230, end parentheses, comma, single quote, 0.0k, single quote, end parentheses, dot, draw, open parentheses, win, end parentheses. New line, text, open parentheses, point, open parentheses, 20, comma, 180, end parentheses, comma, single quote, 2.5k, single quote, end parentheses, dot, draw, open parentheses, win, end parentheses. New line, text, open parentheses, point, open parentheses, 20, comma, 130, end parentheses, comma, single quote, 5.0k, single quote, end parentheses, dot, draw, open parentheses, win, end parentheses. New line, text, open parentheses, point, open parentheses, 20, comma, 80, end parentheses, comma, single quote, 7.5k, single quote, end parentheses, dot, draw, open parentheses, win, end parentheses. New line, text, open parentheses, point, open parentheses, 20, comma, 30, end parentheses, comma, single quote, 10.0k, single quote, end parentheses, dot, draw, open parentheses, win, end parentheses. New line, hashtag, draw a bar for initial principal. New line, height equals principal, asterisk, 0.02. New line, bar equals rectangle, open parentheses, point, open parentheses, 40, comma, 230, end parentheses, comma, point, open parentheses, 65, comma, 230 dash height, end parentheses, end parentheses. New line, bar, dot, set fill, open parentheses, open quote, green, end quote, end parentheses. New line, bar, dot, set width, open parentheses, 2, end parentheses. New line, bar, dot, draw, open parentheses, win, end parentheses. New line, hashtag, draw bars for successive years. New line for year in range, open parentheses, 1, comma, 1, 1, end parentheses, colon. New line, hashtag, calculate value for the next year. New line, principal equals principal, asterisks, asterisk, 1, sorry, just 1, open parentheses, 1 plus APR, end parentheses. New line, hashtag, draw bar for this value. New line, x11 equals year, asterisk, 25 plus 40. New line, height equals principal, asterisk, 0.02. New line, bar equals rectangle, open parentheses, point, open parentheses, x, 11, comma, 230, end parentheses, comma, point, open parentheses, x11 plus 25, comma, 230 dash height, end parentheses, end parentheses. New line, bar, dot, set, fill, open parentheses, open quote, green, end quote, end parentheses, new line, bar dot set width, open parentheses, 2, end parentheses, new line, bar dot draw, open parentheses, win, end parentheses, new line, input, open parentheses, open quote, press, enter, to quit, end quote, end parentheses, new line, win dot close, empty parentheses, new line, main, empty parentheses. If you study this program carefully, you will see that I added a number of features to spruce it up a bit. All graphical objects support methods for changing color. I have set the background color of the window to white. Win.set background and white in the string. I have also changed the color of the bar object. The following line asks the bar to color its interior green because it's money, you know. Bar.set fill and then green in the string. You can also change the color of the shape's outline using the set outline method. In this case, I have chosen to leave the outline the default black so that the bars stand out from each other. To enhance this effect, the code makes the outline wider, 2 pixels instead of the default 1. Bar.set width 2. You might also have noted the economy of notation in writing the labels. Since we don't ever change the labels, assigning them to a variable is unnecessary. We can just create a text object, tell it to draw itself, and be done with it. Here is an example. Text, open parentheses, point, open parentheses, 20, 230, end parentheses, comma, single quote, 0.0k, single quote, end parentheses, dot draw, open parentheses, win, end parentheses. Finally, take a close look at the use of the year variable in the loop. For year in range, 1, 11. The expression range 1, 11 produces a sequel of ints or integers 1 through 10. The loop index variable year marches through the sequence on successive iterations of the loop. So the first time through, year is 1, then 2, then 3, etc. up to 10. The value of year is then used to compute the proper position of the lower left corner of each bar. X11 equals year asterisk 25 plus 40. I hope you are starting to get the hang of graphics programming. It's a bit strenuous, but very addictive. Addictive or not, I've been reading for 42 minutes and I'm tired. So we're going to continue with section 4.6, choosing coordinates, tomorrow. Thank you for joining me. I'll see you in the next one. Good night.